This video will focus on eclipsing binary stars. These are star systems whose orbital plane is aligned with our viewpoint, so that when eclipses occur, there is a dimming of the amount of light that we receive. We will model the binary star systems with light bulbs placed on a spinning platform powered by a battery. The bulbs have internal batteries and 2 luminosity settings. A fiber optics cable points at the binary bulb system from a distance of about 10 feet. This cable feeds into a photometer, which measures the incoming light intensity for the computer. Our fiber optics cable is pointing directly at the eclipsing binary bulb system. We have made sure that all other light sources in the room are extinguished. We turn on both bulbs at the higher setting and send power to the rotating platform. We now start graphing the intensity of light data provided by the photometer. We see the repetitive cycles of one complete orbit repeated over and over. Once an astronomer learns the orbital period of a binary system, they would then combine all of this data together into a light curve representing only one complete cycle of the system. The roughly flat top of the graph represents times when both bulbs are fully visible. Note that the graph minima, known as eclipse depths, are pointy since the bulbs are the same size. The points represent the instance when one bulb completely obscures the other from the fiber optic cable's perspective. Note as well that both eclipses have roughly the same depth since the bulbs have almost the same luminosity. Let's now repeat this experiment with one of the bulbs at its lower luminosity setting, representing a star with a cooler surface temperature. We start the bulbs revolving. Let's see if you can predict what the graph of light intensity versus time will look like. Classroom students should follow normal procedures or instructor guidelines. Viewers not in a classroom should record your vote and explain your reasoning on a piece of paper. Please pause this video and answer the question. We now show the computer and live graph creation. We can see that the eclipses are still pointy, but have different depths reflecting that one bulb is more luminous than the other. The deeper eclipse occurs when the less luminous bulb is between the more luminous bulb and us. We now explore another common class of variation, where one bulb, or star, is bigger than the other. To accomplish this, we'll make use of an acrylic globe commonly used in light fixtures. We place the globe over the top of one bulb, which effectively transforms it into a larger, but less luminous light source, and once again start the platform spinning. We now see that the graph of intensity versus time has eclipses with uneven depths, as expected. But note that both eclipses now have flat bottoms, as it takes a longer time for the globe, or larger star, to transit the smaller bulb, or smaller star. This eclipsing binary simulation shows a fourth broad type of eclipsing binary light curve, stars of similar surface temperature but of different sizes that we can't easily emulate with our demonstration. Note that here we get flat-bottomed eclipses of the same depth. In this graphic, we see all 4 broad categories of the limited parameter space shown in an eclipsing binary computer simulation. Same temperature, same size, which gives us pointed eclipses of the same depth. Different temperature, same size, which gives us pointed eclipses with different depths. Same temperature, different size, which gives us flat eclipses with the same depths. And different temperature, different size, which gives us flat eclipses with different depths. Note that in reality there are a complete range of both luminosity and size values, not just same and different. However, this is a good starting point for exploring how stellar parameters show up in graphs of intensity versus time in the eclipsing binary stars we observe. There are many complexities down the road, like eccentric orbits, football-shaped stars, and star spots of different temperatures than the surrounding surface that can be explored. More teaching materials can be found on the web at astro.unl.edu.